Developers are pushing AI coding agents far beyond generating simple one-shot code snippets. The goal now is long-duration, asynchronous execution, asking an agent to clone entire repositories or build sprawling applications from scratch. The expectation is that you can issue a single, massive command, step away from your keyboard, and let the machine do the heavy lifting over several hours. But if you actually try this, the result you get is rarely a working product. It usually ends up being a broken, hollow shell. Look closely at the output, and you'll find the symptoms of systemic failure. UI buttons don't connect to anything, features remain entirely untested, logic trees are left partially finished and abandoned. This failure stems from the agent's inability to maintain its working state over time, regardless of how well the initial prompt was written. You are hitting a hard bottleneck known as context degradation. And simply throwing a larger context window at the model does not fix the underlying degradation. It only delays the inevitable breakdown. To achieve actual autonomy, we have to abandon the idea of a continuous context stream altogether and build an entirely new execution environment around the agent. This structural shift is called harness engineering. Turning a coding assistant into a reliable, autonomous cloud worker requires a specific state architecture. Without a harness to manage that state, long-term autonomy remains mathematically impossible. This interface represents the baseline of language models around 2022. You were trapped in a chat box, constrained by a 4,000-token working memory. Trying to build complex software architecture within that constrained space meant developers had to stop relying on static prompts and start actively managing the model's memory. This led to context engineering. Instead of loading everything up front, the system dynamically pulls specific data into a tiny window exactly when needed. We built RAG for databases, tool calling for external environments, and MCP for vendor features. Early iterations of tools like Cursor, Aider, and Roo used these methods to read isolated relevant files rather than attempting to ingest the entire codebase. As underlying models evolved with larger context limits, this dynamic data loading allowed agents to tackle longer, more ambitious tasks. But there was a structural flaw. Even with intelligent data retrieval, the agent was still forced to hold its entire working process in a single, continuously running stream. And that continuous stream is exactly what causes catastrophic failure on extended runs. So what actually happens to this dynamic data flow when a task runs for 12 hours instead of 10 minutes? The system falls into the summarization trap. As the agent works, its timeline buffer fills with high-fidelity data blocks. Eventually, hitting hard capacity, the agent executes a mathematical compression, summarizing previous work to free space, leaving behind low-resolution versions of its history. Operating on summaries, original granular code details are permanently gone. This creates severe state hallucinations. A compressed summary might falsely relabel a feature as verified and completed, even if the underlying code is broken. It then builds new features on top of false assumptions, skipping critical steps, generating flawed logic, and dooming the project. Developers initially tried to bypass this by deploying swarms of subagents, each with isolated context windows, but orchestrating multiple agents proved highly chaotic and inefficient. The mechanical failure is linear. The longer the duration of the task, the more summarization cycles occur, compounding logical errors exponentially. Expanding the context window gives you more time, but it does not fix the trap. To permanently solve state degradation, that continuous stream of memory must be severed entirely. To protect the working memory of the model, we have to move one layer above context engineering and dictate a strict environment of execution. Replacing the continuous timeline with the harness execution loop, the process begins with setup. The agent generates a master external production requirement document, a structured JSON file. In step 1, the harness forces the agent to extract just one isolated task. For step 2, the agent is injected into a pristine, entirely empty context window. It has no memory of the previous steps, only the precise context required to execute that specific task. In step 3, the agent writes code, runs tests, and documents results. Finally, step 4. The harness updates the central JSON document with a verified outcome, then ruthlessly flushes the context window entirely, wiping the slate clean for the next iteration. You can observe this exact lightweight architecture driving highly effective open-source projects like Ralph, as well as Anthropic's own harness demonstrations. By decoupling the overarching master plan from the immediate working memory of the large language model, the harness ensures the agent never has to summarize its own past. Context collapse is eliminated because there is no continuous context to degrade. It is critical to understand that harness engineering does not deprecate earlier methodologies. It encapsulates them into a vertical stack. At the foundation, prompt engineering still exists. We use initial prompts to establish the agent's persona. Sitting directly above that is context engineering, which manages tooling and dynamically controls data visibility. And capping the stack is the harness, dictating the strict rules of execution. Finalizing this three-layer stack enables complete geographical and hardware independence. A developer can now open their local IDE, assign a massive feature request, and then completely close their laptop. Because the harness externally manages the state of the project, that execution loop can run securely and autonomously on remote cloud servers, grinding through tasks for hours or even days. Developers now interact with these cloud agents asynchronously, checking in through enterprise API integrations like Slack to receive real-time status reporting. The ultimate end state of this loop is quiet efficiency. The cloud agent simply finishes its iterative work, autonomously generates a final pull request, and only pings the developer when the entire job is mathematically verified. This logic extends far beyond initial code generation. You can configure this automation to check for daily model updates and autonomously maintain live production websites without manual intervention. Strict environmental state management moves AI beyond conversational assistance and into the architecture of an asynchronous, autonomous digital worker.
Thank you. Share and subscribe to Learn AI for more AI insights.